addition to digital machine learning, researchers are now studying whether we are able to also compute machine learning in an analog way, in which case they would propagate light and sound, which are analog and in wave formats, in order to create more efficient machine learning processes. Analog machine learning hardware platforms promise to be faster and more energy efficient than their digital counterparts. Wave physics, as found in acoustics and optics, sound and light, is a natural candidate for building analog processors for time-varying signals. Here, these researchers identify a mapping between the dynamics of wave physics, as in light and sound, and the computation in recurrent neural networks. This mapping indicates that physical wave systems can be trained to learn complex features in temporal data using standardized training techniques for neural networks. As a demonstration, these researchers show that in an inverse designed inhomogeneous medium can perform vowel classification on raw audio signals as their waveforms scatter and propagate through it, achieving a performance comparable to a standard digital implementation of a recurring neural network. These findings pave the way for a new class of analog machine learning platforms capable of fast and efficient processing of information in its recently. Machine learning has had notable success in performing complex information processing tasks such as computer vision and machine translation, which were intractable through traditional methods. However, the computing requirements of these applications are increasingly exponential, motivating efforts to develop new and specialized hardware platforms for fast and efficient execution of machine learning models. Among these are neuromorphic hardware platform, which we have talked about in this channel, with architectures that mimic the biological circuitry of the brain. Furthermore, analog computing platforms, which use the natural evolution of continuous physical system to perform calculation, are also emerging as an important direction for implementation of this research paper. These researchers have identified a mapping between the dynamics of wave-based physical phenomena such as light and sound and the computation in recurrent neural network, or RNN. These RNNs are one of the most important machine learning models and have been widely used to perform tasks such as natural language processing and time series predictions. These researchers in this paper show that wave-based physical systems can be trained to operate as an RNN and as a result can passively process signals and information in their native domain without analog to digital conversion, which should result in a substantial gain in speed and reduction in power consumption. In this framework, rather than implementing circuits that deliberately route signals back to the input, the recurrence relationship occurs naturally in the time dynamics of the physics itself, and the memory and capacity for information processing are provided by the waves, as in light and sound, as they propagate through space. In this paper, these researchers were able to show that the dynamics of wave equations, in this case light or sound, are conceptually equivalent to those of a digital RNN, which is the machine learning model. This conceptual connection opens up the opportunity for a new class of analog hardware platform as opposed to just digital hardware platforms, in which evolving time dynamics play a major role in both the physics and within the data sets themselves. While these researchers have focused on the most general example of wave dynamics, the results can be readily extended to other wave-like physics. And they also further discuss that such an approach of using physics to perform computation may inspire a new layer of platform for analog machine learning devices with the potential to perform computation far more naturally, but more importantly, more efficiently than the digital platforms. The paper was published in the Science Advances journal back in 2019. Having said that, we have made a lot of progress in terms of thinking analog computing in addition to digital. And neuromorphic computing, for example, is one of them that mimics the way in which the brain, human brain, performs information transfer and information analysis at the analog level. And so that's where the mimicking comes in. Having said that, this paper is also important because each paper that is being published paves the way for the future way in which we could evolve the field. Now, while this particular paper was talking about recurrent neural network, nonetheless, it could still be a stepping stone in terms of discussing these type of solutions, analog solutions, for other modeling, computational modeling as well, because we always need to start somewhere. And in this case, they started with RNN, but we could, of course, also expand it into CNNs, for example, for those who are interested in this field. Nonetheless, the most important part to bring about this paper and as papers like this is that there are a lot of us who are thinking more in terms of analog information processing and not only digital information processing, which is extremely exciting for us neuroscientists because we do want to, for those of us who are thinking about or doing more research on the wave-like properties of the brain, in this case brain waves, these type of research are extremely exciting because they start paving the way for us to think about information processing more also on an analog level and not only in the digital realm. I hope you guys like this paper, and that's all I have for today. Thanks for watching, and I'll see you guys next time.